All right, welcome. Today, we're going to tackle a cornerstone of data science and statistics, simple linear regression. It's this really cool, elegant tool that helps us find predictable patterns hidden inside what just looks like a bunch of random noise. Okay, let's get right into it.
I mean, it sounds way too simple to be true, doesn't it? Can we really use something as basic as a straight line to make smart guesses about what's going to happen? Well, you might be surprised, because in a lot of cases, the answer is a huge yes. Let's see how.
Just think about it for a sec. We all kind of feel that higher SET scores usually lead to higher GPAs, right? But it's never perfect. If you actually plot out that data, you just get this cloud of dots. The big challenge, and where the magic of regression comes in, is finding that one single line that slices through that cloud in the best way possible.
So here's how we're going to break it down. First, we'll get the big idea behind predicting with a line. Then we'll look under the hood at the anatomy of that line. After that, we'll figure out how to find the best fit line, see how to grade it, and finally, watch it all come together with a real-world example. Okay, so let's start with the big picture here. This is not just about drawing a line through points we already have. No, the real power is in building a model, like a simple prediction machine, that can take a new piece of info and tell us what it thinks a future outcome will be. And when you boil it all down, this is what we're doing. It's a formal method, a repeatable recipe for finding the exact equation of that one special line that does the best job of summarizing the relationship between two things. And believe it or not, pretty much any straight line you can imagine can be described by this simple little equation. Here, y is the thing we want to predict, like a student's GPA, and x is the thing we're using to predict it, like their SAT score. A and b, they're just the two secret numbers that define our specific line. So let's pop the hood and take a look at those two numbers, A and B. They are the absolute secret sauce that makes this entire thing work.
First up, we've got A, the y-intercept. Think of this as your baseline, your starting point. If our predictor x was 0, this is where our line would start on that vertical axis. It basically sets the stage for all our predictions. And then there's B, the slope. This is the action hero of the equation. It tells us exactly how much y will change for every single step x takes. A positive slope, as x goes up, y goes up. A negative slope, as x goes up, y goes down. The slope is the relationship.
Okay, so we know we need a line, and we know it needs an intercept and a slope. But if you've got a cloud of data points, you could draw, I don't know, 1,000,000 different lines through it. So how in the world do we find the single best one? Well, the first thing you got to wrap your head around is that no line is ever going to be perfect. Real-world data is messy. Our line is a model, a simplification. So there's always going to be some space between our actual data points and the predictions our line makes. That little gap, that error, is everything. And that error actually has a name. It's called a residual. For every single dot on our chart, the residual is just that vertical distance between the actual dot and the spot where our line predicted it would be. Some are tiny, some are big. So here's the absolute key. The best line is the one that makes the total error as small as it can possibly be. To do that, we take every single one of those errors, we square them, which gets rid of negative signs and really penalizes the big errors, and then we add them all up. The line with the lowest sum of those squared errors wins. That's the least squares method. Now, don't worry, you don't have to do this by hand. Computers are amazing at it. But the concept is basically a two-step process. First, the math looks at how the x and y values move together and how spread out the x values are to calculate the perfect slope. And once we have that perfect slope, we use it plus the average of our data to lock in the perfect intercept. So we did it. We found our best possible line. But hang on, is it actually any good? Just because it's the best fit doesn't automatically mean it's useful. We need a way to give our model a report card. And that report card is called R-squared. It's this fantastic little number that's super easy to understand. It gives us a score, somewhere between 0 and 1, that tells us what percentage of the story in our y variable can be explained by our x variable. Let's just look at the two extremes to make this crystal clear. An R-squared of 0 means your line is, well, it's useless. It explains absolutely nothing. On the other hand, an R-squared of 1 means your line is a perfect crystal ball. It explains everything flawlessly. In the real world, we're always landing somewhere in between. So let's get real for a minute. Let's take a number from our source material. We run our regression, we do the math, and we get an R-squared of 0.68. Okay,
So what does that actually mean?
It means our simple little line explains a whopping 68% of what's going on with our data. The other 32%, that's just noise, random stuff, other factors we're not measuring. But hey, explaining more than 2/3 of the story with one straight line, that's a pretty powerful model.
All right, theory is great and all, but let's make this totally real. Let's take the exact data that gave us that 68% R squared and see the final result with our own eyes.
Here are the raw numbers. We've got 6 pairs of x and y values. Just looking at it, the relationship isn't obvious at all, is it? It kind of looks like a jumbled mess. But the math can see the pattern hidden inside. And boom, here's what we get. After the least squares machine does its work, this is the equation it spits out. Our best fit line starts way up at 19.42 and has a negative slope of 1.59. That means for every 1-point jump in x, we predict y will drop by 1.59 points. This is our little prediction machine.
You know, there's a quote from our source material that just nails it. We've taken this messy cloud of data and we've created a clear, precise rule. For any value of x you want to plug in, our line gives you one and only one predicted value for y.
So let's leave it with this question for you. We've just unlocked a powerful method for finding simple patterns in a really complex world, from how much you study affecting your test scores to company ad spend affecting sales. These relationships are everywhere. The only question is, which ones are you going to find first?